robot for last 10 years, and we're moving toward manipulations and other stuff. But today I would like to talk about things I've been thinking about for a while. This is mostly for the leaders of the research center or the industry people, but I realize it's the researchers and at schools and researchers, engineers who are actually working on AI are not exception. We are all biased looking at the AIs or any intelligent algorithm. So I'd like to talk about this topic, and I will start with the importance of physical intelligence. I think it's pretty much obvious at this point. Like, you know, we've been sort of servant, almost like a slave of information technologies. And when it comes to information technology, almost every data is digitalized. It's so very easy to transfer, and it's all about information distribution. How can I get information as easily as possible, as quickly as possible, as efficient as possible? When it comes to physical services, it's no longer that easy because you have to actually deliver energy. No longer you can just send a few bytes can help solve the problem. You actually need to properly execute the task by injecting energy. You have to deal with a lot of non-digitalized qualitative issues in delivery, elderly care, companionship, farming, construction, home security, and so on. Currently, the actual commercialized physical services are mostly in the factories, as you know, and they're fantastic. They can do work much better than human, but they actually don't have much intelligence. They're all trajectory following machine with a very good, very well designed robotic arm. They can follow the trajectory very accurately, very consistently. So when it comes to tasks that cannot be done by just following trajectory, are still done by human, because there's no such an intelligence that can handle these uncertainties and so on. So I've been working on last 10 years or so to focusing on the hardware issue. How can we make a robot more interactive and handle uncertainties? So if you think about all these manufacturing conditions are great for this high precision, predetermined trajectory following robots, because everything is known, and then we create an environment for robot to do that. But when it comes to like a non-factory environment, just like your room or your son's room, everything is changed because you have to move. You could move around because you cannot just install robot everywhere you need the services, and nothing is known completely. So and the situation is very dynamic. So no longer this like trajectory following rigid robot can complete the task. So we've been working on a robot that can do this kind of task for last 10 years, getting inspired by Phantom haptic device. We developed this, we call it proprioceptive actuation. It's a completely different paradigm that allow us to build the robot very robust, and then also do high fidelity force control. So you can see this Cheetah 2, Cheetah 3, mini Cheetahs are all successful thanks to this new innovation and actuation. Recently, we attached our newly developed sensor, which is also developed for last 10 years. We've been working on this for last 10 years. And then we can do things like unprecedented. No other lab can do such a things like this. We can make robot a lot more context aware and high bandwidth. And we're here just as a demonstration of the virtual magnet. If you have a fast enough robot and have a high bandwidth and very good sensor that's robust against impact and immune to acceleration, you can create a virtual magnet between rubber and wood. So the hardwares are getting better in our lab, where we know how to build very good high fidelity force control and so on. But yet the intelligence is really, really lacking. And I'll explain why, and why we misunderstood AI and so on. So this video might be a very good introduction. Probably some of you already seen this video last time I talked about. This is a video of me picking an apple in a bowl without looking at it. So the physical intelligence is a very vague concept because we're really not aware of it. So I'll talk about that in detail. But hopefully that was real time. I'll play it again, see if you can see anything. And in the slow motion, you can see a lot more detail. And to collide, first of all, our hands are colliding with everything all the time because the hands are very good at colliding. And then for some reason, my hand is going to through some decision making and ended up choosing the worst possible choice. And but eventually successfully take it out the apple. In summary, there are 4 or 5 decision making process within this like about a second action, and none of these individual decision makings are that optimal. I'm not even sure what kind of quantitative sensation, the quantitative cost function I can even guess. But we're very, very robust against this like small failure and then recovering from this. Some might think that that's a very successful aggressive. I see actually multiple failure within this 1 second video, but the humans are very excellent on recovering and then doing certain tasks very, very reliably. You've probably seen many cases like that. If you are wonder, just bring a key from your pocket and then see what your hand is doing. You're very we are very good at dealing with the things without having clear quantitative goal. So with that motivation, I mean, I can show you another video. I'll show you that video later. Very similarly complex tasks can be done by just saying that clean tray. So I'll come back to it, but we are excellent at doing services not very well defined, not necessarily easily done by robot. So there are many tasks we want to tackle, but our like understanding or of our AI or how we see things in the task world is very biased, and I want to talk about that kind of issue. And I actually wrote this article in Naval Labs blog, Forward Thinking, and the IEEE spectrum. You can also see it from the IEEE spectrum, and I sort of found the root cause as instantaneous anthropomorphism. So humans are, we are a very social animal, and then we understand things based on how we understand from other people. It's very important to understand what other people, some people call the mirror neuron. Some people call that as a mirror neuron is a main mechanism of empathy. We have to understand based on human term, and which is our evolutionary power, but at the same time that actually can cause a lot of misunderstanding or biases when we actually look at AI, when we face AI, because AI is the algorithms we develop are a lot more vague. It's not very clear unless you know every single detail going on behind it. Nowadays, machine learning, large neural network is very hard to conceive as a human, even though you are the one who designed it. So this three topic, I'll go through one by one, and then we'll go back to the examples and then go back to the anthropomorphism I'm talking about here. One of the best example in instantaneous anthropomorphism is happened in this kind of video. You've probably seen this video. Boston Dynamics robot has excellent balance capability. This video is probably 2011 or so. It's very early on. When this one published in the YouTube, every engineer working on robotics are like, "Wow, this is amazing!" But if you look at the reply on YouTube channel, written by most like non-engineering people, half of them at least are criticized about like, "Wow, you're so mean to the robot. The robot is going to be so angry, or later the robot is going to revenge you," and so on. But if you really think about like a second after that happened, your brain also perceives the aggressiveness of the engineer because you have to actually inject quite a bit of energy, and then the struggling of the robot, and then you feel a little bit of empathy, right? Followed by like your engineering reasoning came in like, wow, it must be amazing algorithm. The robots are built really well. But before that happened, your brains are programmed to notice this the motion pattern, like aggressiveness, or how big the agent that is aggressive is, or the how the robot is responding. Before even thinking about the robot is made out of aluminums and the machine, this is something anybody's exception. So as long as you're human, you have to perceive that, and then that occurred in your brain. Some people call that as is reflex behavior, reflexive cognition. And somebody like Daniel wrote even book about how humans cognitive processes are separate by like fast actions and then slow thinking, and then some of the fast thinking actually surprisingly significantly impact and how we think and how we judge and so on. So some people even make fun of those people, like showing emotion, like, well, this is a piece of metals, and then somebody wrote program, why do you even feel empathy? But we can't really say that they're like not knowledgeable or so, because this is just a human reflex, and then we cannot be free from it. The main important point is that we have to aware that we are like this, we are programmed like this, so that whenever you see some demos or whenever you see some AI action, we have to have a filter that about what you feel and what your assessment. This will keep on happening. This is what I call the instantaneous anthropomorphism that like human innately have whenever we see or observe some data. So the first topic is we judge the performance of AI comparing to human capability. Hans Moravec and Rodney Brooks, Marvin Minsky, they already talked about this in the 1980s. Not necessarily with the comprehensive reasoning. I can provide a little bit of more reasoning about it. Like they say that it's completely easy to make computers do some like adult level intelligence tasks, like playing checkers and seemingly difficult tasks. But it's very difficult to do like a small 1-year-old when it comes to perception and mobility. So they compare with the intelligence task with the perception and mobility. You can't even see that even these the ancient AI gods have a very biased expression about task. Anybody notice here? They will use language intelligence task for playing checkers, but they didn't say intelligence task for perception of mobility. That's exactly one of the biases I'm talking about here, because those tasks like the checkers and chess or Go or writing mathematics, because those are difficult for human. We see somebody who does well, we call it intelligent. We don't call people somebody can bring up key out of your pocket and then open a door intelligent, because that's so easy for us. But if you're looking from the AI's perspective, that's a very wrong perspective, a very biased perspective. Wrong might not be the right word. So, but you have to be aware of this. Like we are judging the performance of the robot or some AI technology based on what human is doing, like based on what human is good at. We developed like backflip in the mini cheetah, and then so many people love it, and then they get impressed. But if you really get into the detail, that backflip controller took like 3 days to develop, and then we didn't even touch it. That walking video on your right, that took like years of research, just walking around, just balancing, not falling. Seemingly much easier than backflip, but it takes like much longer. It's actually a lot more difficult technology, a lot more sophisticated intelligence. Yet, including the professors who's working on Lego robot got so much more impressed by the backflip, and then that instant emotion. You can't avoid it. You can't clear from it. You cannot be free from it, because we are still animal. We still have that instantaneous anthropomorphism. We are biased by what human can do, what we are impressed about when you see the human. When you see human walking around, nobody's impressed. But when you see somebody's backflip, we're much more impressed. Well, let alone dog. If you see a dog backflip, you're probably very impressive as well. But these are all based on our innate evolution of our cognitive function. We judge based on what we understand about human, what we learn about how we learn from other people. So that kind of bias or the cognitive function apply exactly to the robot when you see. So you have to be aware of it when you're developing controller, when you decide your task. Sometimes you can take advantage of it, like us. We want to design something not easy to develop, but to maximize the factor, impressive factor when we demonstrate robot. But it can be very dangerous if you're directing a research direction, or you're allocating like research funding if you're a government worker, for example. So, this is exactly the going back to the Hans-Moravec's paradox. We see this AlphaGo, that's amazing intelligence. It is amazing intelligence, and the Go playing is such a large, almost infinite cases, very complex tasks, and writing mathematics, playing chess. Those are very difficult for human. But when it comes to like making shoes or washing dishes, we don't call that intelligent behavior, even though we can't even do it. We have we have a computer, an algorithm that can beat any human being in Go playing or chess very easily. But we don't have a single intelligent algorithm that can do the dishes that like my 7-year-old can do it. So this is basically the bias that we're talking about. And then that make us ignore the actually important technologies that I call physical intelligence that, allow you to make a shoes maybe, or well, the shoes are made very differently nowadays, but, doing more tactile behavior. Maybe driving car can be somewhere in between, but there's a lot of complicated discussions about how to even quantify that cost function and so on. So that's a first bias, probably one of the most very common bias among the researchers. And second thing, it's not necessarily bias, but it can be bias. Probably one of the most difficult challenges for us. We are actually making decisions a lot of times just qualitatively, and whereas computer need number, we can't even communicate with the computer without number. When I say qualitative, sometimes actually quite binary. We judge based on, oh, that's good enough, that's good, that's not good, let's do it again. It's very binary, but it's still very qualitative. So this is the dilemma of cost function. If you working on any machine, any algorithms, you cannot free from cost function unless you're working on some categorization or some machine learning that without cost function. But if most of people using the reinforcement learning, or even the learning from the data, you need to have some cost function. But if you are actually researchers like the graduate student, you will know that's a proxy. That's never going to be real cost. I've been working on leg locomotion in model-based control and machine learning controller. And our cost functions are always based on body motion tracking. It's about state, and then distance from the state to our desired state. And or some variation or some combination of it. Is it really the right cost for running well? You can argue many different ways, and then we still don't believe that that's the same. Running well, what is running well? Like run fast, turn fast? How about not falling? We don't call that like run really fast and then fall down. That's not running well, right? It's very qualitative, but somehow we know what is good enough, what is not good enough. And but when it comes to leg locomotion, that body motion tracking is a pretty good proxy of cost of running well. But when it comes to other tasks, it's becoming a lot more vague and then not very clear. Like, many manipulation tasks, manipulation spaces are like I can't even compare, like a much bigger than leg locomotion, because leg locomotions and manipulations are actually quite similar in the duality, because locomotion is about you're walking on an object, and the manipulation is actually you're actually manipulating the object. And locomotion, the object is actually flat all the time, most of the time, because you're walking on the earth on the flat ground. But manipulation, the object shapes are all the time. Your gravity directions are not even constant. And a lot of tasks like a cleaning, you can't really create a trajectory tracking cost to complete it. It becomes very complex. I'll show you a couple of examples. Make a sandwich. How can you create a trajectory of each fingers to make sure you create a sandwich? This is exactly the comparison from the factory robot. Factory robots are designed to finish everything based on trajectory. They don't even know they finish properly, but it's fine because everything is controlled environment. When it comes to safe driving, what is a safe driving? How you quantify clearly safe driving? Grocery shopping. I asked a bunch of computer science engineering students, like, a lot of people actually believe that everything can be quantified. And I asked, like, what did you buy last night? Did you go grocery shopping? And yes. And then I said, so what did you buy? And then they say, buy bought this. And then I asked, like, what quantitative basis do you use to choose those grocery shopping? Why did you choose that for tomato? It's organic, and versus the other one? We don't have any quantitative basis. We are using very vague qualitative information or unknown information, and make a decision based on good enough. Cooking, social tasks are even more complex. And if you really think about the difficulty level of certain tasks, AI tasks or controller tasks, it actually depends on how easily the goal is quantifiable. The goal is very easily quantifiable. Like if you can create a very good proxy of the cost function of the cost, then the things are much easier. Things are less easily to quantifiable tasks, then it becomes suddenly very difficult. This is gonna haunt us, and then this is gonna be one of the most big challenge in AI in the future. OpenAI, the Rubik's Cube is really impressive, the work, and there's a lot of great work there, like domain randomization, like the friction range and so on, that trained over many different uncertainties. And its cost is based on the final result. That's why you see all these inefficiencies, because each finger doesn't exactly know what it's doing. There's no detailed abstraction there. Only the final abstraction, final goals are abstracted properly, and that's easily quantifiable. But can you think about the same thing as a cooking? It's not as clear as a Rubik's Cube and have a clear color on it and a clear state, and then how many degrees you have to rotate to finish the task. It's become suddenly very vague. I'll ask you the challenge: write a cost function to cook the thing that in your picture well. Again, I'm not giving you a number, like, the score of that cooking should be more than 90 degree, 90 score. We can't really even say that. So think about that challenge there. And again, same video, I'll show you in slow motion. Because you cannot see anything if you see in real time. And think about, like, what will be the right cost function to maximize to do this task well? Would you train based on the final result and then throwing like 100 cameras to look at every single spot to check any dirt left or the volume of food ingredient left? I'm not even sure how to collect those data, and then how you distinguish from the droplet water and so on. And the hand is not even like staying in this object. I'm not even sure there's grasping, how many grasping action is. It's almost like hands are like sliding against, like a skiing on this object. And it's very dynamic. And somehow we can execute this very vague task, like a clean tray, such an abstract concept. Without going through any quantitative basis, we actually can execute it. So I'm pretty much agree with I'm agreeing with the person, several biologists, and then this is one of the philosophers who wrote about this, and then he studied about evolution, and then they're basically saying that nature evolution is not optimization process. You know, nobody can prove it. It's only opinion. And then he give you a lot of examples. For example, the two biggest deer is fighting against each other to find the mate, and then not always biggest one find the mate, because when two biggest the leaders alpha males are fighting, and the small one is having mate, because during those big ones are fighting. You know, there's always like you know, to find the example that, you know, the not the fittest survive, it's just good enough to survive. So the challenge becomes when we are trying to program robot to do some like very vague tasks like cleaning or cooking. We need to program in a way that the robots can do such things based on the good enough principle, not necessarily following the optimal cost. Again, another example, like, you know, bring a cup of water to your mom. Like, you know, if you ask a robot to bring a cup of water to your wife, and what quantitative basis become really meaningful? Like a minimum time, maybe, yes. Minimum trajectory, minimum the pathway, so you can go faster, yes. Are those that important compared to not spill things in front of the inside of the refrigerator, or not closing doors, or putting things in the right places? There's a lot of things that you shouldn't do. You should not do to satisfy the okay sign, rather than minimizing time, minimizing trajectory. I don't think that's that important. As long as you can deliver within 5 minutes, that's another good enough principle. So usually these okay sign is you know, done by graduate students are writing hand-coded the constraint. Don't do this, don't do this, don't do this, don't do this. And then you optimize this cost function within that safe space. But the safe space is not created automatically. It's all hand-coded by grad student. So how do we do that more automatically? We can't do that without understanding abstract concept before programming the abstract concept. So the quantifying the abstract concept is the key challenge in many, many tasks. And, you know, one of the biggest bias actually cause all this. Actually, we just don't know what we're doing. You know, a lot of physical tasks we're doing every day, like chewing carrots, and somehow grinded carrots in your stomach. And have you even noticed what your tongue's function while you're chewing carrot and talking with your friend is really complex task? We're not even aware of it, because a lot of tasks like picking an apple in the bushel, you don't need to be aware of it. It's pretty much automatic. By the way, this action happened in like a second, and then I saw apple in my hand, but I have a zero recollection of what my index finger was doing, what my thumb was doing, and was I changing the target apple in between? Like, I have no idea. You'll probably experience it all the time because you are not aware of it, because that's much better for your brain. That's why we don't even have a proper language to describe this. Like easily spread, like, you know, spread peanut butter jelly, peanut butter in the bread. And like any verb actually you're using to describe things, and when you ask your son to do anything, just stop a moment and think about the verb and how difficult to quantify those things. We don't even have enough specific word to describe this action. And that might be the first step for us to tackle this physical intelligence, because we never need those languages, because we are actually learn very easily by looking at somebody else's doing. Some people believe that that's because we have a mirror neuron, we can see it and we can execute it. If you think about like we're using this camera, like our eyes looking at somebody else's doing and copying is incredible. It's not like a 3D motion capture, like, you know, some have, and then you can kind of somehow extract that out, join and the angle trajectory, and then execute your arm. That's not how it works. We just look at it and then we can somehow copy it. This is actually really amazing technology, but we were not aware of it. That's why we never developed those languages to even describe these details. Yet that's gonna be big trouble. So this is a fun YouTube video. Their father is trying to teach us, the kids, to be more specific and organized.
Do you guys
I will show you some of the part.
think you can write down some instructions and teach me how to make a peanut butter and jelly sandwich?
Yeah.
Step 1. Get 2 pieces of bread. Step 1. Get 2 pieces of bread out. Got 'em. Get a butter knife and get some PB. Take 1 piece of bread, spread it around with the butter knife.
No, Dad, with the peanut butter.
I'm just doing what it says. It says take 1 piece of bread, spread it around with the butter knife.
Hold on.
Get some jelly, rub it on the other half of the bread.
No, Dad, open the jelly.
Well, it doesn't say to do that. Put the breads together on top of each other. Take a big bite. Do you guys think you can write down some instructions?
Sorry, I had to make it extremely specific.
Oh, good. I'm starving. Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar. With the knife, scoop a bit of peanut butter out of
That means like a lot.
A bit means a lot?
In my world.
All right. There we go.
Doing better than before, though.
Open the jelly jar. Squeeze it onto the other piece of bread.
No.
So I think you got the idea. I don't need to even point out all these detail. Like, see how vague. I mean, the father is giving a hard time intentionally, but even the best instruction, the father was like, okay, you did a good. Every single verb, if you look at it, is not even well specific because we are okay with it. And then now we are in big trouble because when you write program on the computer, the computer has absolutely no common sense. We have to be a lot more specific. I said, clean the room, and then it put the 2 pillows in a certain way. I don't know even how to specify that. And then when you put down all this note together, you have to be good enough to be gathered and so on. Somehow the slide is not advancing. You know, my personal ultimate challenge, like elderly care in the future, it tasks become very, very physical and can be very subtle and very difficult. Even using human, they have to constantly discuss, like, move your body here a little bit, like, okay, you can hold on it, just trust me. A lot of vague language has to be used to actually deliver, do the task properly. So I hope these kind of biases can be useful. And then I hope you guys actually think about this when you are actually working on your task, your research, and then thinking about the directions where you should go. So this is the last slide. So I'm open to any questions if you have any time. I'm not sure time where I spent probably about 30 minutes, but we can also discuss during the panel discussion. Thank you very much.